Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my pleasure to introduce Francis David. Francis David is a PhD candidate from University of Illinois at Urbana-Champaign. You're supposed to get your PhD in August sometime. So he's interviewing with the security part of the distributed system and security group, and he's going to tell us about some of his work on how to exploit hardware features to undermine software security.
Thank you, Helen. So good morning. And like Helen said, I'm going to talk to you about how some hardware features can actually undermine system security. And none of us can deny that there's been a rapid growth in hardware technology. There's been really progress from single-core CPUs to multi-core CPUs of today. There's the GPUs in computers have gone from 10 million transistors to 100-fold increase in that number. And there's been work on actually even doing computation on these GPUs now. So there's lots of cores, there's more features, there's lots of complexity. And a lot of this is configurable. And all of this gives you tremendous opportunity. There's a lot of opportunity to build really interesting systems. But there's also huge opportunity here for malware. Since this complex hardware has significant state information, there's so much configuration settings, and it's highly configurable. There's lots of debug features that are left into the hardware, and there's lots of unused functionality as well. So if you take a typical cell phone, the actual hardware in the cell phone supports a lot of functionality, and there's many timers. There's lots of specialized features on the phone, which most operating systems don't end up using. The operating systems tend to be general purpose operating systems. So if you take Linux, for example, it doesn't really exploit every single feature that's on these mobile phones, for example. So there's lots of unused functionality. There's also unexpected behavior of hardware. Sometimes the hardware behaves in ways that you don't really expect. So what I'm going to talk to you today about is two different tools. Essentially, they're proof of concept attacks, which demonstrate that hardware features and behavior can be actually exploited in order to build malware. And the two projects I'm going to talk to you about are Cloaker, which essentially exploits hardware features in order to provide a malicious rootkit environment. And the other thing I'm going to talk about is BootJacker, which essentially exploits memory preservation, DRAM memory preservation in order to break into a system. And that essentially brings us to the outline of today's talk. It's a long talk, so I'm going to spend most of my time on the Cloaker rootkit work, and I'm going to give you a brief overview of the BootJacker work, and before concluding and talking about some other topics. So let's start with Cloaker. And I'm not going to take complete credit for the whole thing. This is definitely joint work. The paper wouldn't have been possible without my colleagues at the university, Alec, Jeff, and my advisor, Professor Campbell. And what we are looking at here is rootkits. And to put the notion of rootkits into the right perspective, I have this picture here that essentially shows you a typical attack scenario. So the attacker first has to break into the system. There's essentially exploiting some sort of design flaw or an implementation flaw, or like just brute force password cracking or social engineering attacks just to gain access to the system. Then the next stage is somehow maintaining control over the system, and that's where the rootkit comes in. So the attacker removes all the traces of the break-in and installs the rootkit. And that's going to be kind of the main focus of today's talk. On the Cloaker part of it. And the rootkit essentially provides a platform in some sense for performing malicious activity. And that's stealing passwords, financial information, or running bots for spam, or just using it as another platform to attack others. And so I'm not going to really talk about a vulnerability in the system that an attacker is going to use to break in. I'm assuming there's going to be some vulnerability, and I mean, it's well known. There's lots of different platforms today that there's always some vulnerability. The iPhone was broken into. Linux phones from Motorola have been broken into. So I'm not going to talk about how to break into the phone, but I'll talk about how to maintain surreptitious control. So in order to put this rootkit that we built into perspective, there's lots of other folk who've been researching rootkits and malware. And rootkits initially started off being user mode applications. So there were these user mode binary programs that would replace system files on your computer. On a Linux system, for example, the program that displays the process list would be replaced by this other binary, which would hide a malicious process, for example. And then rootkits moved on to being kernel mode when system defenders, essentially security researchers, started figuring out ways to detect user mode rootkits, and so on. There's been stages of development, and all of this has essentially been driven by advances in detection technology. So there's this continual struggle between the good guys and the bad guys, and so that kind of drives this evolution. And let's look at each of those stages in a little bit more detail. So the user mode rootkits, like I said, essentially are modifications to user programs. And when such rootkits were found in the wild, the detection techniques that people came up with were essentially to ensure that the integrity of the system files is preserved. And so they built integrity checkers. And there's also like traditional antivirus signature checking type of tools as well, which check for malware signatures in various files in the system. Then so once there were easy detection techniques for user mode rootkits, the malware guys resorted to kernel mode rootkits, where they would insert kernel modules, modify the kernel in various ways. And there are two distinct categorizations of such kernel mode rootkits as well. So one class of such rootkits modifies kernel code, and these are kind of easy to detect. Again, you can just use the same signature or integrity check kind of ideas and apply them to the kernel space. And the other type of kernel mode rootkits manipulates kernel data, and these are more insidious. So they would essentially manipulate some state in dynamic state in the kernel, and detecting these by integrity or signature checks isn't sufficient. So researchers came up with lots of anomaly checkers, which check for odd behavior in the system. So looking at the system from two different perspectives, for example, a high-level view and a low-level view, and seeing if they match. So studying and trying to extract some anomalous behavior of the system. And they've been pretty successful at that. Modern anomaly detection techniques, essentially, they've shown that they can detect a lot of these existing kernel mode rootkits that are out there. So the next step. Firmware rootkits were proposed a couple of years ago, and essentially they work in the same way as kernel mode rootkits while normal operation. The firmware aspect of it is just for persistence, so that they can remain in the system through a power cycle operation. And this is essentially done by white hat researchers, and they essentially show that you could have such rootkits reside in the BIOS of the system, the ACPI or the PCI BIOS, and so on. And then Sam King pioneered the work on virtualization-based rootkits here at Microsoft Research, in fact. And the idea there is to run the rootkit, the malware, at a layer lower than everything else that's running in the system. So you move the whole rootkit to the virtual machine monitor and run the rest of the system as a virtual machine. And people have argued that maybe such rootkits aren't that big of a deal, because I mean, there are techniques that one can employ just to check for the fact whether or not you're running in a virtualized environment, and that would hopefully kind of indicate that there's something wrong in the system. So maybe detection of virtual machine-based rootkits just reduces to the problem of detecting if you're running in a virtualized environment. And like I said, Subvert was one of those rootkits. Bluepill is another rootkit that uses AMD's hardware virtualization support. And to be fair, only these first two types of rootkits have been seen in the wild today. It keeps popping up. But the firmware rootkits are, wow, do not show this message again.
No.
Oh, no?
Yes.
Okay. Maybe I can just turn it off. Okay. So to be fair, only those first two types of rootkits have been seen in the wild today. And firmware rootkits, virtual machine-based rootkits, and what I'm going to talk about are all completely the work of white hat researchers. You know how always people say that you have to be one step ahead of the bad guys? Right now we're 3 steps ahead of the bad guys, so that should be good, right? So what I'm going to talk to you today about the Cloaker work is a hardware-supported rootkit, which essentially operates similar to a virtual machine-based rootkit in the sense that there's no modifications that are done to the OS or the applications. And the way it survives is by only modifying hardware state and settings. So it manipulates all these register settings in hardware, flips bits and so on in order to survive. And since there's absolutely no dependency on any of the host OS services, it has to provide its own environment for malware. And by kind of essentially divorcing itself from the rest of the operating system, it can totally evade any signature checkers or integrity checkers or anomaly checkers, which are only looking at the operating system. So in some sense, such rootkits essentially exist in a parallel world from the operating system. And that brings us to how do we build such rootkits. So Cloaker, which I'm going to talk about today, is built for Linux on the ARM platform. And like I said, it has to provide its own mini OS environment essentially for running malware. And I'm going to talk about a couple of malware payloads later on. And the services that Cloaker provides are like a typical operating system. It has memory management support, interrupt management, and it has even networking support. And Cloaker is a non-persistent rootkit. So since we're talking about a phone here, we argue that having a persistent rootkit on the phone, a non-persistent rootkit on the phone is fine because people rarely let their phones die from loss of battery power. So people usually keep it charged. But if you need to go into persistence, we have to modify some part of the system, which opens us up to detection. You had a question?
I do have a question. So you said that this will not be detectable by anomaly detection.
Yes.
So will it slow down the execution of the, I guess, think of it as primary OS on the phone in any way?
So the way we've designed our current rootkit, it does slow down the execution of the primary OS in a little bit, and I'll show you a slide later on that shows the amount of the slowdown. But there's ways to bypass that as well, and we've discussed that aspect of it, and it boils down to the notion of there are 2 things you can do. One is actually how do you measure time, and if the time source is from a local timer on the system, the rootkit can modify the time source. If it's like an instruction counter that can be modified as well, the rootkit can modify that. So that it can come up with counter defenses. The other thing that we've been also discussing is since this is a cell phone system, it has to have power management. So we came up with the notion of essentially running the rootkit just when the OS is going to sleep. So at that point, by definition, nothing else should be running on the system. So there should be no other software monitoring tool that's going on. And the rootkit can actually run when the system is sleeping in some sense. So there are other approaches to countering that problem. And I will talk about that later on as well. Another question. Oh, you can have, if you have another question.
Okay. With both of those answers I find unsatisfactory. With the first one, you said, or maybe it was the second one, running while powered down, then you're trading off the battery resource. You're consuming more battery. And with the first one of virtualizing time, that assumes that you're not dealing with somebody who can have access to the network as part of their detection code.
Yes.
And so both of these seem, saying, I'm going to assume that that I get to take the last step in this game rather than my opponent.
Yeah, you're right. So the question is, the point is, it's like a continual battle here. So if the good guys come up with a particular solution, the bad guys come up with a counter solution. And that's what we're talking about here, right? So
I assume that this is
the last step.
detectable once I take if I get to take the next step?
In some sense, yes. So if you have the last say in it, then maybe. And yeah, yes.
But if the person creating the rootkit has the last say, it always has the last.
That's always the usual case as well, because.
But in that case, I don't think that's a worthwhile assumption, because if you make that assumption, I can find out what the code is that is supposed to be doing the detection and just make sure it always returns no rootkit. So, right, because if you set up the game such that the attacker has the last move, the attacker then knows what the checker software is and can just make sure it modifies the code so it always returns no rootkit.
Oh, but the checker software could also be protected by hardware, and it may not be easily modifiable. So we are even talking about scenarios here where the checker software you have a complete root of trust right from the hardware to the checker software. If the checker software is only checking the integrity or signatures in the OS, it's still not going to be able to find our rootkit. And in cases where the rootkit would modify the OS, the checker software, if the root of trust is from the hardware, the checker software cannot be subverted. So you see what I'm saying? If the checker software has been authenticated from the hardware, and it cannot be subverted, even if the rootkit were running in the OS.
We'll take it offline.
Yeah. So I was talking about ARM all this while, and essentially the reason we looked at ARM was because ARM powers a lot of mobile devices today. And it's not just these cell phones, and it also has like GPS devices. It powers the Ford's Fusion system and so on. And there's also going to be an explosive growth in such devices. Yes?
Is your technique highly specific to ARM?
So by nature of such, the design of such rootkits is very tied to the hardware, because I'm talking about hardware features. And our particular rootkit is tied to the ARM platform.
So I don't mean, have you written lots of assembly code for ARM? I mean, are the things that you exploit specific to the ARM processor and not, say, Intel?
Yes, almost. There could be similar parallels in other architectures, but certain things that we exploit are very ARM specific. What we are trying to do here is essentially to bring out this notion of a class of new malware, which is hardware supported. And this is just one instance, and I'll show you another example later on as well, but we're kind of trying to bring out this notion of this existence of this different class. So like I said, there's going to be a whole number of such devices on the market. So there's going to be 4 billion cell phone subscriptions in a couple of years, and this is, analysts say this, and that's kind of almost one phone for every 2 people on the planet. And in contrast, the number of PC users is just going to be like 1/4 of that. So it's a platform that has tremendous impact. And it's not just mobile devices and cell phones. A lot of consumer electronics, toys even, use this processor. So the reason I have the slide is that it shows that the domain we're targeting is significant. I think I probably skipped over a slide, but what we're looking at here is essentially a slide that shows how our rootkit operates. There's essentially 2 things our rootkit exploits. One of which is flipping a bit to redirect interrupts. And the way this works is on the ARM platform, the ARM9, there's 2 different locations at which the interrupt vector can reside, at the 0 address or at this high address here. And a bit in a processor configuration register determines where the interrupts get dispatched to. And typical operating systems like Linux or a couple of other ARM-based operating systems we looked at relocate the interrupt vector to the high address so that they can map the slow address to a null page, and which kind of helps in debugging, so that if there's a null pointer dereference, they can easily, during development, they can catch it and fix it. So they always map the 0 page to a null page, and they have the interrupt vector up there. So what Cloaker does is it first flips that bit the other way so that interrupts start getting sent back to the low address. And now the other question is, how does Cloaker manage to get that page mapped in without modifying the OS page tables? And the way Cloaker does that is it inserts a locked TLB entry. And this is a feature that's on the ARM processor, to answer your question. And so it inserts a locked TLB entry, which the OS has no way to even go and read. The ARM doesn't provide support for the OS to go read these TLB entries even. And this locked TLB entry can essentially map in arbitrary regions of the physical address space into virtual memory. And so these addresses are virtual memory addresses. And what happens here is, now that Cloaker flips this bit and inserts a mapping for the 0 page, it can go put in an interrupt vector at that 0 page to redirect interrupts to itself. And this essentially brings down to your question, where it's intercepting every single interrupt now. And so what we do now is, we don't want to slow down the system significantly. So what we have here is, for interrupts that are critical, time critical. So for timer interrupts, we would just do really quick pass-throughs to the OS. We don't interpose on any timer interrupt path. We would only interpose on interrupts that are very asynchronous, like a network interrupt or like a keyboard interrupt or something like that. So which essentially gives you a little bit of protection against timing-based detection. And when you run malware code on asynchronous paths, the OS really doesn't know when to expect those interrupts. So it still just delays it by a little bit. Yes.
So you said you inserted a locked TLB entry, which is what prevents the system's page table of knowing about the existence of the memory where the rootkit is running, correct?
The locked TLB entry essentially avoids modification of the OS page tables.
Right. So, but then what prevents the system from actually allocating a page in the memory space where the rootkit is running?
Okay, so that's the next slide. I think I'll get to that in the next slide. Yes.
I have a question. You just said you choose to inject your payload when certain kinds of interrupt happens, like a network interrupt or something. But on the other hand, have you thought about you just choose to inject your interrupt based on some timer you
control
about the CPU? Because for most interrupts, I think they just execute the critical part with a small amount of code, so it doesn't make a difference between a network packet arrival or some other thing, right? The critical part is very short, so then they just give the control to the CPU, so that won't make a difference.
I'm not sure I understood your question. So are you saying that it's okay to intercept all interrupts, or?
I'm saying
Is
it's
it
okay
even bad to intercept?
to inject your payload not based on the type of the interrupt, but based on a pacer you keep.
Okay. A pace that you maintain. So that's definitely possible. One thing that we still are able to do with our rootkit is enable any unused timers, for example, that are on the board. And one of our payloads actually does that. And that would give you a very controlled pace to do your to do whatever malware work you want to do. So it depends on how much extra unused functionality is there on the system. And there's one in our case, in our platform, the Linux kernel uses 2 of the system timers, and the 3rd timer can be used for malware. Okay. So to get back to the other question, let me just cover the other part first. So how do we insert this rootkit? We essentially use a kernel module for installation, and you could think of other really stealthy ways of inserting the rootkit by directly accessing physical memory through the dev mem device on Linux. But right now, for this proof of concept, we just use a kernel module where you just do a module insert and a module remove, and that kind of inserts the rootkit. And to answer the other question, where does physical memory come from, where does the actual rootkit reside in memory. There's several places to do this. One is essentially to use on-chip SRAM. So on these mobile platforms, it's usually a couple of kilobytes of on-chip RAM that's used for fast execution or for like power management, and you could use that portion of memory. Or the other thing you could use is NAR flash. NAR flash is I don't know if you know about this property of NAR flash, but NAR flash allows you to actually execute code off of it directly, just like you would do from normal memory. So unlike NAND flash, which has to be accessed in blocks, NAR flash you can actually execute code off of it. So you could use memory map NAR flash. The other thing the simplest thing we can do is essentially just allocate some memory inside the kernel in our module, for example, and just cause a memory leak in some sense. So I mean, it just looks like a memory leak inside the OS. So there's several options. We just picked the simplest option. Use just kmalloc. Does that answer your question? Yes.
So you have to do that in another module that's left loaded, right?
No, I mean it's like a memory leak. So you can insert the module, just don't free it. Okay. The next thing I'm going to talk about is the services that are provided by Cloaker. So Cloaker is just the hiding mechanism and an operating environment. It has to provide a couple of services. We wrote a service for dynamic memory management using the buddy memory allocation algorithm. Eventually, we discovered that we could write a lot of payloads without using dynamic memory management. And so it's an optional kind of payload, but it's still there. And we also have interrupt management support in Cloaker. It would let payloads independently enable disable interrupts for different devices. For example, if they want to monitor a particular device, they can. The library also supports lookup for the current interrupt numbers and allows malicious payloads to essentially register handlers for those interrupts. And Cloaker also has networking support. And this is not complete networking support in the sense that it doesn't have the complete TCP stack in there. It essentially lets you do IP communication. And the way we do this in Cloaker is we use a really stripped down version of the Linux kernel's Ethernet driver. So the intuition behind this is you don't really need code for initializing the device or tearing down the device, a lot of these different types of functionality. All you need is a routine that lets you send a packet and a routine that lets you receive a packet. And you can write these, you can rebuild this really small network driver in some sense. And once you have these two mechanisms to send and receive packets, you can achieve IP networking by discovering two parameters, which are like the gateway MAC address and the source IP address. So if you have those two parameters, then you can start sending out network packets. And the way we discover those two parameters is pretty easy as well. So we intercept periodically we intercept some incoming network packets. If we pull off a packet from the network card, the OS doesn't see it, but it's treated like packet loss on the network, so it isn't really a big deal. Yes?
Is there a reason why you have your own Ethernet driver rather than just hooking the OSs?
So the reason we didn't want to hook the OS is not modify any part of the OS. So we didn't want to, oh, you're talking about actually using the OS code directly? Yeah, so that's definitely another option that we've also looked at, to just use the code so you don't even have to have local code. In our case, we had to make some modifications so that it doesn't interact with the OS driver in weird ways. So the same OS driver, the OS driver that's in the Linux kernel does a bit of locking and so on, which we can't reuse in our rootkit because it modifies OS state.
Why you can't just hook the packets as they come up from the system into like the IP stack or at any layer of the stack, just redirect the calls inside the kernel?
So the only thing we can do is actually go read a packet if it's in an OS buffer. We can't really modify the OS control flow in any way because that opens you up to so if you have to modify control flow, then it opens you up to all those other detection techniques.
It's relatively easy to detect you're doing that now by checking the page tables or going to interrupt just seeing what address you jump to.
I didn't get your question.
So currently, things you've described so far, like moving the interrupt vector down, down to sort of like the 0 address. The OS can detect that trivially, right?
Oh, yeah.
Making a page table. I mean, like an issue I'm prepared to start making modifications to the system.
So the OS can,
I mean, you know, I just really released Linux plus one that has these 3 instruction checks, which will get most of this.
So you're right. I mean, there's one bit that we flip, right? And if the OS goes and checks for that bit, you can essentially detect our rootkits. That's what you're saying, right? In some sense.
Exactly.
Yeah. So that's definitely true. So what I'm trying to bring out here is not that one particular vulnerability exists. I'm saying that there's a class of such vulnerabilities, and in a couple of slides I'll show you another technique that doesn't use that flipped bit mechanism. And so Cloaker is just a proof of concept that it's trying to demonstrate that this class exists. And it's not about this particular vulnerability. You can't place your finger on this thing and say, well, this bit is flipped, and therefore, if I go check for this, I can avoid this class of rootkits, or this class of malware. So I'll show you in a couple of slides another way to do this, the subversion that doesn't use that bit. So we do get that question a lot, so which is why we came up with the other alternative. More questions?
So can you interrupt the moment when the operating system is reading that specific bit? Can you interrupt?
Can I interrupt the moment when the OS is reading that pretty specific bit? So the other attack I'm going to show you can actually let you do that. Right now we can't, because we're not interposing on any OS read operations at all. So we're not modifying. We can possibly insert a TLB entry for that. Actually, the bit manipulation is essentially a hardware instruction. So it directly reads it off a processor status register. So it's very difficult to intercept that request. So unless you're intercepting that whole page that instruction exists on and trying to subvert it, it's more complicated. There's an easier way to do it, and I'll show you in a minute. Other questions? Okay. So getting back to the IP networking part, so we intercept a couple of arbitrary packets off the network. We have this packet header buffer inside Cloaker, which has pre-filled in entries for things like the destination MAC, the source MAC, and the destination MAC has to be the gateway MAC, and that needs to be figured out. The source MAC can be read from the Ethernet card, and it has the IP header fields and so on. And the way we fill up this packet header is that once we see an intercepted packet that's coming from a different subnet, we just copy the source MAC off into the destination MAC here, which is actually the gateway MAC, and we copy the destination IP address, which is the source IP address, so that way we get the source IP address. The other alternative is to go mess with the OS structures, but this kind of gives us a little bit of OS independence at least. And that gives you complete IP networking. Yes?
But you're limited because you can only send things out of the network. You can't attack any of the local network.
You cannot attack?
In other words, like that, you set that MAC to be the gateway, which means you can't attack any of the local devices on the network now. You can only attack ones that pass beyond the gateway.
Yes, you're right. So this is just a simple illustration for how you would essentially send out information from the host. If you wanted to do some such thing like that, you could probably implement ARP locally as well. So it's up to you how much functionality you want in the system. The other thing I'm going to spend some time talking about is the keylogger that we have built as a payload for Cloaker. So these are a couple of payloads that I'm going to talk about now. And this one intercepts input on the serial port. And this is like a typical serial port. We're considering an NS serial port that's standard on all PCs as well. So they have similar things on phones. And these serial ports work by having a FIFO buffer for the transmit and another FIFO buffer for the receive. The problem here is now that, say you want to intercept this input that's coming on the serial port, keystrokes. The problem here is that this chip doesn't let you put back something that you just read. So if you read from the receive FIFO, it would essentially shift all the other content, and so it's like a shift registers, and so you read this character out, and there's no way to put this back in again. So this initially kind of led to some issues, and we were figuring out how to do this key logging without so that the OS also still receives that character. So you don't want to read a character off and the OS not receive it. Yes.
What's the interface on most phones for the keypad if you want to intercept, if you want to implement Keylogger?
On the phones, there's a specialized bit of hardware that we haven't really looked. I mean, on real phones, there's a specialized bit of hardware that we haven't really looked at. So this keylogger works on this prototype cell phone board that we have, and on real phones, I'm not sure what the exact hardware is.
Do you feel like you're taking advantage of a weakness in the serial port?
Yeah. So what we're doing here is going to take advantage of a weakness in this particular chip.
Serial ports for input on most mobile devices.
Yeah, you're right about that. So what we're trying to do here is, again, a proof of concept as well. So we're showing that in this particular piece of hardware there exists this vulnerability. On the prototype hardware that we were looking at, this was the only way to get a keyboard input into the system.
So coming back to John's question, so this particular case you cannot run the Rootkit in sleep mode. You have to.
Yes, you're right. So this has to be, you're intercepting the keyboard input, which means you delay the input by a little bit.
Yeah.
Yeah, so we didn't have access to, to the real hardware on a phone for the keyboard. We didn't have the specs for that component. But I'm sure there's probably some similar debug feature in that can be exploited. So the way we do the serial port debug, exploit is that we enable this debug feature on this chip, which lets you loop back the transmit lines to the receive lines, and this is used for debugging. And we essentially, the way we operate now is we read all of the input that the user types in, and then set this loop back feature, write it back out, and then unset that feature. So that essentially lets you intercept input, and while still letting that input pass on through to the OS. Yes. Okay. So the other possibility here is to directly find and access OS buffers, and again, this requires understanding the OS internals. And while it's a possibility, we just thought this was more elegant. So we wrote another couple of payloads. We wrote.
What happens if there's something comes in at the exact same time you got the feedback?
I'm sorry? There's.
Okay, so if I understood this, so you're going to read out of the receive buffer loops, use the loop back to send back through. So.
Oh, what happens if there's something coming in?
Yeah.
Oh, we're looking at human input here. So the speed at which you can do the loop back, read out, and everything is really fast. And
okay. So you've lowered the probability, but not removed.
So if you can type, we can type 2 characters within microseconds, then it's. I'm not trying to essentially say that this works for a generic serial port interception at the max. Yeah, that's. Yes.
Does this have a bit as well that you can check for to see if the debug mode is turned on? Similar to the.
Now this one, in this case, we essentially turn on the debug mode, loop back the input, and then turn off the debug mode. So this one you wouldn't even see. So the other 2 payloads that we wrote were like a payload that does essentially a distributed denial of service. So it activates an unused timer, like I mentioned. There's some bit of hardware that's unused. So whenever it gets a notification, it'll send out a packet using the networking support. And the other thing we did was essentially send out the keylogger buffer as soon as it's full. And the problem with, as soon as you have network packets being sent out, now you're vulnerable to network intrusion detection systems. And we're not going to really delve into that. But essentially, once you start doing externally visible changes, you're opening up yourself to detection. So I'm going to now move on to the actual evaluation system, what we did. So what we, the whole thing was designed and built on the OMAP H2 platform. It's a Texas Instruments board for, it's a prototype cell phone essentially. And it has an ARM9 processor core. It has, I mean, we use the latest Linux kernel. The real version doesn't really matter because we're kind of divorced from the OS. We can run with any Linux kernel. And the measurements that I'm going to talk about now are, like, we measure the size of our rootkit. We also look at the performance impact on the OS, to answer your previous question. And I'll also look at detectability and compare existing approaches and other rootkits as well. So for the size aspect of it, you can see that we managed to write Cloaker in a really compact manner. So essentially, this table says that Cloaker is really, really small. You can actually have Cloaker fit within those couple of kilobytes of SRAM, for example. And in our case, we managed to fit all of Cloaker, including its payloads, within the first 8 kilobytes of memory. And the reason for this is we don't really have to have that much device driver support, and our payloads are simple as well. So it's a trade-off. If you want more complexity, you get larger size. But what we try to show here is that you can get significant levels of malware, essentially. I mean, you're still able to send out network packets, and you're still able to intercept keystrokes. And you can now do all of that in a really compact manner.
I'm curious, for example, so the denial of service, the IP denial of service. So what does that 12 lines of code look like?
So the 12 lines
packet over the network.
So all it's doing is she's sending a packet over the network. So so you're assuming a pre-configured attack target, and it's not, there's no control component yet.
One line of code that's the byte array, byte vector, that's the payload, okay?
Yeah.
And so then the other 11 lines?
So there's code that's essentially looking up the interrupt. I mean, the timer interrupt comes in. For the denial of service payload, essentially, there's a timer interrupt that comes in. The interrupt management system processes it and gives it to you. So there's also code to, like, enable that additional functionality, that extra timer.
So maybe 3 lines there. I'm having a hard time figuring out how you can possibly talk to a NIC enough to get it to send out a packet in 12 lines.
Oh, so the 12 lines doesn't include the actual network code. So that's included inside Cloaker. So the actual network interaction, the driver.
So some of those 147 lines of the network driver. That's
Yes. So this 147 lines of code includes all the services that Cloaker provides. So the networking, the interrupt processing, and the memory management, we left it out separately. So it's really easy. I mean, it's really small because, like I said before, you don't have to have all the code. And to answer your question before, so we took out the Linux driver and stripped out a lot of code from it. So we couldn't reuse the Linux driver. Okay, so the performance question. So what does this whole thing do to performance? So this shows a bunch of statistics that are reported by Imbench, and you will notice that there is a small noticeable change in performance when you're running Cloaker because it's intercepting interrupts. And yes, this definitely does open it up to detection in some manner, and like I was discussing before, it's a continual struggle here. Yes?
Is your processor having content of power modes, and could you fool the user into thinking that it processes a lower power state than it was?
So you're talking about, like, dynamic voltage scaling. On the ARM that we're looking at, it doesn't have any dynamic voltage scaling. But the other attack I'll show you in a minute probably also avoids this issue at some level. So detectability. So what I have here is a big table. So there's a lot of information in it, but essentially this columns lists all the existing techniques that are used for rootkit detection. So you have integrity checks of the disk, or like the process, platform integrity checks, kernel integrity checks. So I'm including anomaly detectors for the kernel inside this category, and the signature checkers. The takeaway from the slide is the only thing that can actually go and be able to detect Cloaker effectively is if you do a complete physical memory scan and search for the signature. Yes.
What do the VMM detectors do?
The VMM detectors? Yes. Oh, so the VMM detectors essentially check for the presence of TLB entries that are being used up in the system by the VMM. So this was a paper by folks from Stanford and VMware, and the paper was VMM detection, myth or reality. And yes, that's the HotOS paper. So they have a whole slew of such methods that they use, and TLB sizing is something they kind of run in order to see if there's TLB entries that are missing. Yes.
So with regards to non-persistence, doesn't non-persistent mean that disk process integrity checkers or signature checkers shouldn't be able to find that? So for user mode, you have user mode non-persistence, you have disk process signature checks.
Yeah. So if you check the signature of the process, of all processes, you'll still find it, right? So it's a user mode process. So you can think of this as like you running a user mode process and deleting the file, right? So it's not on the disk. If you run an integrity check of the disk, you won't find it. A signature check of the disk, unless you're checking all disk blocks. If you're looking at the file system, it's not there on the file system anymore because you deleted the file. But you'll still be able to, if you look at the process itself, you have the process list. So it's all in user mode. And a kernel level detector can go through all the processes and look for signatures. Yes.
You can go first.
Okay.
Yes.
Okay. Can you explain why the VMM detector can detect VMBRs but not Cloaker? Because in some sense, Cloaker, I can run Cloaker, I run a VMBR as Cloaker.
You're right. You're right. So the reason that Cloaker is not detectable by those VMM detectors is that, at least for this TLB sizing, for example, right? When we use those locked TLB entries, the locked TLB entries on the ARM are an exclusive TLB. So you're not using up the normal TLB entries that are available for the OS. So there's 8 TLB entries that are specifically reserved for being locked down. And those are not used by the OS, and then that can be used by Clobber. So the OS will still see no changes in the TLB entries.
But there are multiple ways in the VMM detector paper. You are just talking about one method in the detector that cannot be used to detect Clobber.
Yeah, right? I think it's right. I think, I'm getting very critical here. I think specifically what you're saying is, yeah, x86 VMM detectors are not appropriate for catching ARM.
Yes.
Right? But if you read Tal's paper, basically what they say is, and I think you've got the exact same problem here. You've basically built a VM rootkit. I have a hard, it's an ARM-specific VM rootkit instead of an x86-specific rootkit, but it is a VM rootkit. And
so the thing here is,
I think if you look at every single one of the techniques you've talked about are detectable in the same sense that the x86 ones are. It's just they're ARM-specific. Your interrupt thing, your TLB. Surely if I was going to write the paper on how I write a VMM detector for the ARM, one of the things I would say, well, I should write through all of the locked TLB entries, for example. Right?
So you're right. So the thing we're arguing here about is essentially, so I'm arguing that there's one thing you can do in order to detect VMM-based rootkits. So you can put your finger on this thing and say, I will do a check for a VMM, and there are definite ways to do that. So there's one thing you can do, and I can detect all VMM rootkits.
No, I don't. I think Tal's argument in the HotOS paper was that there isn't one thing that you can do to detect every kit, but there are enough things that it is a cat and mouse game, and inevitably you will be able to find any rootkit that is in existence. You will be able to find. That's Tal's argument.
But I mean, there's one thing you can definitely do in order to detect that virtualization you're running in a virtual machine, right? You can do TLB sizing. There's one thing you can do. So my argument is essentially to say that there is no one thing that you can do that will kind of totally cover the whole class of hardware-based malware. So for the VMM rootkits, if you do TLB sizing, you can say that I can detect that I'm running in a virtual machine, and that's it. So I've come up with a detection scheme. There's no further question on this topic anymore, right? I've placed my finger on that and I'm done.
That's clearly not what they said in the How to Ask paper.
Well, I guess we can discuss this offline. Okay. Yes.
So just to clarify, since there are 8 of these protected via virtual memories, protected TLB slots, you can just do a resource constraint test if you're the OS to see whether all 8 are available to you.
Yeah, right. So I mean, so what you're essentially saying is that there has to be hardware level integrity checks. You have to check the integrity of the hardware in some sense, right? The hardware state. And that's what we argue for as well. So, I mean, we're kind of saying here that it's not sufficient to check the integrity and the sanity of the OS. You also have to go and check the integrity of the hardware as well. So you have to consider the system as a whole, both the software and the hardware parts of it. So we have this argument about checking for the flip bit, right? So let me just go ahead and give you another alternative way of doing this this control flow subversion that doesn't use the flip bit technique. So like I said, I've been stressing here, individual vulnerabilities aren't the topic of this talk. So I'm not trying to say that this particular vulnerability exists. I'm trying to say that this class of hardware-based malware that's possible. And I'm essentially arguing that there's no one thing that you can place your finger on and say this is going to detect all hardware-based rootkits. These generic techniques are probably going to be ineffective. So the other technique I'm going to show you now is using the Harvard architecture for the cache. So there's a separate data and instruction cache, and we use cache line lockdown support in the ARM in order to do this different attack. So what we do is we take a line in the data cache, lock it down, and we lock down the correct values, the OS instructions in the data cache. And in the memory, we actually replace those OS instructions with our malicious instructions. And once we do this, essentially, you have the malicious code that's getting executed because it goes to the instruction cache. But if the OS or any detection technique tries to do a checksum or a signature check, it will not see the malicious code because all of those operations go through the data cache. And that's locked down. So again, this is another case where I'm exploiting a feature of the hardware, the architecture, in order to hide the malware. Yes?
Do you see easy ways to break this as a checker?
And so I'll talk about the mitigation techniques in a couple of slides. Okay. So moving on to countermeasures. So what we are essentially saying here is there's lots of these possible ways you can have hardware essentially enable malicious software to operate, and we have to have some sort of a way to completely check the integrity of the hardware. So one way to do this from software, you still need some hardware support in order to ensure root of trust, but once you can ensure the integrity of these checkers, you can build this framework where you have each driver export a checking function that checks the integrity of its associated hardware. And this essentially kind of gives you a way to check integrity of various components of the hardware. And the drivers are the right places to put these checkers because the drivers are what really understand the hardware. So this is a software-based technique. The other things that are possible are, yes?
Could you give us an example what the check should look like?
So for example, in the driver for the processor, for example, right, or it would essentially have a checker that checks for the integrity of the state in the processor, and that would check for this flipped bit, for example. So I mean, these are functions. So the R framework essentially just uses like return values in order to signal or flag that something is wrong. So these are functions that just check some hardware. There's no specific way you need to write this function as long as it returns yes or no, whether or not the hardware matches the state which it expects or not.
And you need at least one additional checker to check these checkers integrity.
Yes. So the check management. So like I said before, we need some sort of a root of trust from the hardware. So like a TPM kind of system. Okay. Yes, so I'll quickly move on to the other thing as well. So this is the last slide I had on this thing. So you can also do some hardware-based techniques in order to detect such rootkits. And the last couple of notes I had here were, if you have a more sophisticated version, you can also start interpreting OS structures and do more damage. And the thing about this rootkit is it's really hard to write because it interacts with the architecture at a really low level. So it definitely discourages script kiddies. So I'm going to move on to the next section of my talk, and I should be able to finish in half an hour. And that's about the other tool that we did, which compromises systems using forced restarts. So the observation here is volatile memory is not really volatile. Alex Haldeman is going to present a paper at Unix Security in a couple of months where he shows a technique to extract encryption keys from memory after pulling out the DIMMs and putting it in another PC and just imaging the memory. And it's not really a new thing. As far back as 1979, people have looked at this problem, and they've shown that you can actually have this memory persist for a whole week, in fact. And the thing here is you can also revive a complete system, and this is a paper that we wrote. It was published at Unix technical conference middle of last year. And we show that we can use this volatile memory preservation property to revive a system that's been locked up and has been reset by a watchdog timer. And we essentially did it for reliability reasons. But it's much more interesting to look at it from a security perspective. And what I'm going to show you in the next couple of slides is kind of like an illustration of how this attack would happen. So say Alice is working on her computer. She has a couple of applications opened up. There's banking applications, or essentially she's opened up secure connections to various places. There's a VPN that's running and so on. And she walks away from her computer temporarily, locks the screen. And Trudy walks in. She has brief access to the computer, and it's a locked screen. What does she do? So what Trudy does is, now she has BootJacker. She forces the computer to restart in some manner, either unplug the power, put it back in, or use some OS support, and plugs in BootJacker as an alternate boot medium. And what BootJacker is able to do is it's able to revive the complete existing system that was running before. And since it starts up at a lower level, now it can go and switch off any sort of access control mechanism that was in place. So it can disable the screensaver lock, for example. So that kind of gives you the overview of the attack. We didn't really do it for Windows like I showed there. We implemented it only for Linux right now. And so the requirements for this whole attack are you have to have physical access to the system. Secrets have to be in memory. There's no point in trying to revive the system if there's no encryption key or there's nothing interesting in memory. And there has to be some way of restarting the system. On the Linux platform, you have a sysrq key combination. So it's a magic key sequence that you can hit in order to immediately restart the computer. You can also power cycle it. And you also have to have an alternate boot path. So you should be able to boot from a different device. And you can have that support either from the BIOS, or if there's a bootloader, the bootloader could also let you do booting from a different device. And the memory shouldn't be significantly clobbered by the BIOS. So if the BIOS, while it's booting up, goes and erases all of memory, the attack is worthless. And it targets Linux-based operating systems. So let's look at assuming that all the other requirements are okay, let's look at the BIOS memory clobber behavior. Yes?
So is there a specific secure system that is less secure, that was considered to be more secure than it actually is, and that this research has uncovered that it is not that secure? Like, is it that when I don't know, when I lock my machine, I assume if somebody has physical access that they can do something?
Yeah.
Just because I've read about USB-based malware.
Yeah, but for
maybe there was, what is it?
So say for example you were using, you're aware of all such, you are aware of theft essentially, and you rely on encrypted disks and you rely on VPN connections, tunnels and everything in order to kind of really protect your information, even in the face of theft. So you assume in some sense that once I have an encrypted disk and I've locked my screen and everything, I've hibernated my system and I've walked away, that if somebody still steals my laptop, they still won't be able to get to my disk, because when they boot it up back again, you need to enter your password again in order to get to your data. So what I'm showing here is that you can still get to secure data as well by reviving the whole system. So and I'm showing here that the problem isn't new. Like I said before, Alex is going to have a demonstration at using security where he has a way of retrieving the keys. What I'm showing here is a way to revive the whole system. There's no need to look for any keys at all, because you can just use the applications directly. So you don't have to search for anything. You can revive the complete system.
So do commercial systems that do hibernate and have the encrypted disk, I don't know, I think we have one, do they not encrypt memory?
For hibernated systems? So some hibernated systems on the Linux kernel, some of them do, some of them don't. The newer ones do. In this case, we didn't actually even look at hibernated systems. We just looked at a screensaver lock kind of protection. So as long as it's just sleeping, you open it up, there's a screensaver lock, and your keys are still in memory. So if there's authentication, if you walk away and it still requires authentication in order to get your keys, then our system is ineffective against such architectures. Yes?
Would it be sufficient to protect your system to, when the screen is locked, to dump the keys and then have the login authentication regenerate the keys?
Yes. So the attack we're essentially exploiting here is essentially ability to access secrets in memory. So if there's no secrets in memory, it's worthless. Okay, so in order to study the bias behavior about clobbering memory, we wrote a tool that's on a CD. You can boot it up and it'll write a pattern to memory, reboot, and then check if the pattern exists. We ran it in a whole bunch of systems, and interestingly, Dell laptops are totally wipe all of their memory for some reason. And the attack is totally ineffective against any Dell laptop, and I have a Dell laptop. But ThinkPads all ThinkPads, even the newest ones, preserve a lot of memory. So there's very little memory that gets erased.
BIOS overwrites it before
Yeah,
you get to
actually, Vista BootJacker requires, or logo, they require the memory to get overwritten on restart.
by the BIOS.
By the BIOS, yeah.
Okay.
So Dell does it in all their systems. And so the memory that I'm talking about here is only extended memory, everything about the 1 megabyte boundary. Everything, the first 640K of memory is always used up by the BIOS while it's running, and it totally messes it up. For the Linux, on the Linux platform, the first 8 megabytes are reserved for like ISA card DMA, so the Linux kernel doesn't really use up that memory, and which is why we're able to revive the system. And all the clobbered memory in the first 640K doesn't matter. So these are a bunch of different laptops and a desktop that we tested this on. And so there's two aspects to this attack, right? There's first thing is how do you revive the software part of it, and how do you revive the hardware part of it, because it is a reset and the hardware also gets reset. So the software resuscitation, the goal is essentially to resume execution of the software environment, and what we do is essentially come up with a processor context that we just restore on the CPU, which lets the system, enables the system to continue running. And for our attack right now, we assume that we are using the Linux sysrq magic key to reboot the system. It's by default enabled on all Ubuntu-based systems and a couple of other distributions as well. So you hit alt-sys RQB and it immediately reboots the system. And what we do here is in the revival code, we go through the stacks, find the stack in which the reboot handler was called. So this is very operating system specific attack. So it needs to know the layout of the system and so on. And so it finds the stack and it essentially creates a context that makes it seem like this reboot function returned without actually rebooting. And we verify that if you do that, the system actually continues to work. And so while reviving the system, we had to also find the page tables for the process that was running and enable those page tables so that the system doesn't crash as soon as it's as soon as you restore this context on the processor. So for the hardware resuscitation, we looked at. I'm not going to say that we revive all the hardware on the system. We looked at some set of hardware, and the thing here to note here is, it's sometimes Linux automatically revives some devices for you. For example, the disk, we didn't really write any code for that, and it's part of the internal recovery mechanisms of the operating system. So Linux automatically reinitializes the controller and it revives the disk. So we don't have to do anything for the disk. Even the network cards, after a little bit of timeout, it would do it. What we did, we sped it up a little bit by forcing the timeout to occur faster. The display, if it's a Linux-based system, you can always switch to a text console before running the BootJacker tool. Once it revives it back, it's back in the text console, and then you can go back to the graphic console, and that reinitializes the display. And the parts that we actually had to write code for was actually reviving the FPU, enabling the FPU, and this is on the x86, and enabling the interrupt controller, system timers, and the keyboards and the mice. And this is essentially very architecture specific, and this is not done automatically by the OS. So some things we can rely on the OS to fix, some things we can't. We wrote a couple of payloads for this thing as well. Simple payloads essentially which kill a process, which we essentially use to kill the screensaver process. And we did another payload which spawns a root shell, which invokes the shell command on the system with super user privileges. And this would essentially end up being on a virtual console on the Linux system, which is unused. And you can switch to a whole bunch of virtual consoles on a Linux system by using a couple of keyboard combinations. And to evaluate BootJacker, for the correctness test, we ran a lot of applications and interrupted these applications in between to see if they resume execution correctly. We did GCC, gzip, wget, JPEG encoding, AES encryption, and all of these applications continue to run and complete properly after the reboot. The other thing we looked at was, of course, since we revive the whole system, we do get access to any program that's running. So just to prove the point, we ran arbitrary secure programs. You open up an SSH connection to somebody else. Once you reboot, the connection is still open. Or a web browser session. So if you have a banking session open, you can reboot, the lock is gone, and you still have the banking session open. We did it with VPN connection. We also did it with Linux software-based disk encryption technologies. And the key point to note here in this thing is essentially, unlike key retrieval attacks, which you need to go look for a particular key, you have to figure out how to use it. You have to have completely different support to do anything useful with those keys. And there's no need to tailor the attack for a particular key size or any such small detail. So since we drive the whole system, everything is available to us. And as for countermeasures, so you would think that securing the boot process may be enough. So if you look at the requirements that I had before, there's this requirement for an alternate boot path. And I would argue that securing the boot path or even just doing memory clearing in the BIOS doesn't really help that much, because you can do a memory imaging attack, just like what Alex did. So he took out the DIMMs, put it somewhere else, and revived the system. So you can always move the memory modules to a different computer. ECC is interesting because we never managed to get ECC memory to to retain its contents, so it was always reset. And that was, Alex also reports the same behavior. And hardware-based solution is probably something that's more appropriate here. There's colleagues at the University of Illinois. There's actually Karthik, who's actually going to be here for a postdoc position sometime soon. He's working on this notion of a secure coprocessor, which essentially has all the secrets. So as long as you make sure there's no secrets in volatile memory, we can essentially avert this attack. Yes?
Why can't, as a countermeasure, I just have the other authentication factor be something like the user's password and encrypt all of the memory? Then there's no key in memory.
Okay, so if you're essentially tying your authentication for the login with the memory, yes, that's definitely a possibility as well.
No, it won't work. It will work for process specific programs specific to this user, but if you have any server process running in the background, it's still.
But assuming it's a single user desktop, his solution is definitely. So as long as you encrypt the whole system and it's all tied to your authentication ID, you're fine. So essentially the thing we're exploiting, like I said before, is as long as the secret's in memory, we can get to it. There's nothing in memory. If it's all encrypted, we can't get to it.
So the hardware that you're taking advantage of is this interrupt that lets you restart the machine and leave the memory, right? That's sort of the topic of this, right?
Yeah, so the hardware behavior, the memory behavior, the remnants behavior. So we're at the conclusion slide, but I have a couple of slides after this as well, and I have time. So what I've been talking to you today about was a couple of exploits of, I guess, some of a class of security gaps which exists the boundary between architecture and system software. And similar attacks can also exist at other operating systems and other hardware. We haven't looked at it, but there's other people doing work on this as well. There's a recent news article about somebody looking at the system management mode on x86 to do something similar. And they've been talking about the same thing as well that we did with Cloaker, where they run a separate operating system. Totally divorced from the existing operating system as well. And essentially, system designers should consider such possible attacks when they're designing secure systems. So before I conclude, I just want to talk about a couple of, just briefly overview of some of the other work that I've been doing in my PhD. And so I did a lot of work in OS dependability. We first looked at how we use exceptions for error handling. We looked at OS lockup recovery, which from watchdog-based resets, which kind of led to the BootJacker attack. So when you actually pose this as a security issue, it seems to raise more eyebrows. But we did talk about it at Usenix ATC. And the other thing that we're doing is building an operating system that's using hardware isolated and micro rebootable components with state management. So when you're talking about micro rebooting these components in a microkernel, you have to be careful about the state that's maintained in each of these components. So if you take a component that has, say for the example, the network stack, if you arbitrarily reboot that component, if there's an error in that component, what happens is all the existing applications that are using networking will fail because all the state is lost. So in our system, there's a networking stack that's completely restartable because all the state for each individual session is isolated in separate places in memory in these green things here, and the states are mapped in and out on demand using hardware support. So those are a couple of other things that we've been working on, and the idea was in hot deb. We are hoping to get the final paper published somewhere else. And as far as future work, I've shown you a bunch of these vulnerabilities. I'm sure there's lots of more vulnerabilities that are possible in multi-core architectures. A lot of debug features in these systems. I was reading, for example, about the Spark architecture. It provides support for essentially injecting faults and simulating faults. It would take a processor offline if there's this many faults that happen in the system. So if if such multi-core systems let you, for example, offline a core, then, and if malware can exploit that and actually make the OS think that it's offline the core, but actually runs the malware in the other core, it's a possible attack vector. So there's possible things there. We haven't looked at it in too much detail, but it's something that that's worth looking at. And exploiting hardware virtualization support, and now that you can also do computations on the GPUs, you can think of ways that you can probably maybe have malware running on the GPU as well. I mean, not everybody is going to, I mean, they're all going to have the NVIDIA cards, but not everybody is going to use those NVIDIA cards for general purpose computation. So there's a wealth of possible venues here for malware to exploit. And we need to look at defenses for such attacks, come up with hardware, software solutions. Mostly, it has to be a collaborative solution mostly. And the other thing that I've been tying with is essentially to come up with a way to evade intrusion detection systems that are running on a computer by having user space process directly interact with the hardware. So if it's memory mapped hardware, you could still use these TLB tricks that I was talking to you about in order to give a user space process direct access to hardware. And by not using the OS API, which is where the monitoring is done for typical intrusion detection systems, that could give you a little bit more stealth in some sense. And that's another idea I've been toying with. And I guess I'm pretty close to the end of the time, so I can take more questions. No questions? Okay. Okay, thank you very much.